Hello, and welcome to our final physics project, The Movie Mistake. The goal of this project was to find a movie or a TV show, find a scene from said movie or TV show that has potentially interesting physics, explain why the physics in that scene doesn't make sense. We then have to explain what would actually happen in that scene if it was following proper laws of physics, and then we have to present situations where the physics would actually work in that situation. So I'm going to be running through these four because they're relatively short. And then my buddies Manny and Robert are going to be giving you guys different scenarios which would make more sense in this case. So the movie that we decided to go with was Captain America Civil War. Most people, when they think of improper physics and Captain America, they would immediately assume that we're going to be talking about his shield because he can throw it at whatever he wants. It'll bounce off of 7 different objects and it'll come right back to him. But we decided to stray away from that and go with a different scene, which is this one. We chose this scene because I realized that while looking at it, there's a man flying away in a very powerful machine, which is a helicopter, and somehow the fact that Captain America is hanging on the bottom, it causes enough weight to bring the helicopter down to the ground, which doesn't make sense to me. So we ran through step by step the physics to see whether that makes sense or not. And what we learned in this class, the first step that you need to do is you need to draw a picture. In this picture, I have 4 very basic forces, which are the force of the engine causing the helicopter to go up, the force of the gravity of the helicopter coming down, the force of the Winter Soldier, the man inside of the helicopter, also weighing the helicopter down, and then the force of gravity of Captain America weighing down the helicopter as well. So then we just had to plug that into an equation and see whether any of that would make sense, because the only way for this to make sense would be if all of these forces of gravity either equaled the weight of the force of the helicopter going up, or was greater than it. So in this slide, we have our givens, which is the force of the engine being at around 22,000 newtons. We looked that up just from finding out what kind of helicopter he was flying. The mass of the helicopter was around 1,173 kilograms. The mass of Captain America was almost 100 kilograms, and the mass of the Winter Soldier was 117 kilograms. So those are our givens for the equation, and the equation was a very simple F net Y equation because we're only focused on the fact that the helicopter goes up and then eventually goes down. So then we would plug all of our forces from the previous photo into our equation, which would end up looking like the force of the engine minus all of the forces of gravity. All the forces of gravity are minus because they're all going down, which would mean it has a negative symbol. You could also rearrange it to make it look like this to see whether all the forces of gravity would either equal or be greater than this, but for the sake of convenience, I'm just going to keep it in this format. So then to find the force of gravity, you would just take the mass of the object and multiply it by gravity, which is a constant given of 9.8. So then after plugging all of that into the equation, we find out that F net of Y would still equal a positive 8,424 newtons, which means that that force is going up, which wouldn't make sense at all because of the fact that in the scene, Captain America catches the helicopter and then it starts to drop. So what would have actually happened if there was proper physics in this scene was he would have jumped, caught the helicopter, but then the helicopter would just fly away because Captain America himself does not weigh enough to bring the helicopter back down to the ground. That just doesn't make sense.
So with all of our forces combined and weights combined, we have a Y net of 8,415 newtons upwards. And that's the force that Captain America is going to need to overcome to bring down this helicopter. One way to increase force downwards is just to increase mass. And to increase mass, we can use our force equation of force equals mass times acceleration and change it around to mass equals force divided by acceleration. And assuming that we're on Earth, we'll use our force of 8,415 and divide that, by 9.8 to get a mass of around 858 kilograms. Captain America can't just eat a big breakfast and expect to increase his weight by 800 plus kilograms. He'll need something a little bit more than that. He's very strong, so we can assume that he can lift 800 plus kilograms with ease. So bringing along this weight should be no problem for him. Osmium is the densest non-radioactive element, and osmium has a density of 22,590 kilograms per meter cubed. We have the mass of our object. Now we just need to figure out the size, and we have density. Volume is described as mass divided by density. So we take our mass of 858 kilograms and divide that by 22,590 kilograms and get a volume of 0.038 meters cubed. We can convert this to centimeters, which would be 38,000 centimeters cubed, and one side of this cube would be about 33.62 centimeters. This cube diagonally is about 47 centimeters, and that's slightly larger than the diameter of a basketball hoop for a frame of reference, which is 45 centimeters, so you're not dunking this cube anytime soon. Now that we have our cube, we need a strong bag to help carry this cube. This will work. So with this bag and osmium cube, this is still not enough force to pull down the helicopter. It is enough force to keep it from lifting off, so the helicopter is not going anywhere at this point. Now, even the tiniest amount of downforce at this point would bring down the helicopter, and luckily for Captain America, he had a large breakfast that day that put him over the threshold of force, allowing him to pull down the helicopter.
Alright, so another option, instead of changing Captain America's weight, is picking a different helicopter that has a different max takeoff weight. This is the Airbus AS350 that we saw throughout the film, which has its max takeoff weight of 2,249.818 kilograms. This, on the other hand, is the Robinson R-22, much smaller helicopter having a max takeoff weight of 621 kilograms. When it comes to doing the math, we still have our normal FG for Captain America, our normal FG for Bucky Barnes. We do have a different FG for the helicopter, though, which is now 399 kilograms. As well, we throw in our new max takeoff weight, or FE, of 621, and we put all of that into our FNet equation. When we put everything in to our base FNet Y, we get a long string of numbers. We can take all of those FGs, move them to the other side since they're negative at the beginning, which makes them all positive. When we condense all of those, we have our 621 kilograms for our FE and our 616.72 kilograms for our combined FGs. When you subtract all of our FGs from our FE on the other side, it gives you 4.28 kilograms before total engine failure. If we had 4.28 kilograms more weight added on to this, then the helicopter wouldn't be able to take off in the first place. So if everyone had a really heavy lunch, probably wouldn't go anywhere. However, for our scene, it works perfectly. It gives the engine just that little bit of grace period so that it can try to get up into the air. And that leaves Captain America, who has to sit there and kind of fight it for a little bit.
Thank you for watching our video. I hope you learned something interesting about the physics of gravity and helicopters, and I hope you have a wonderful day.